Hi, everybody. Welcome. So this question was asked for me to do. So this is number 34. I forget what homework it's on, but it's chapter 3. It says, on Apollo 14 mission to the moon, astronaut Alan Shepard hit a golf ball with a golf club improvised from a tool. So the free fall acceleration on the moon is a sixth of its value on Earth. So that's essentially, if it's essentially 10 on Earth meters per second, then it's just going to be 10 divided by 6, which is something. Let's see, it was about 5/3. I think it's about 1.67. So we'll say that the G on the moon is 1.67 meters per second squared. All right, suppose the ball is hit with a speed of 25 meters per second at an angle of 30 degrees above the horizontal. So let me underline some of those stuff. There we go. And they want to know how long was the ball in flight? So, all right, here we go. I'm going to, so I already drew the problem right here. I drew a diagram of it. So I'm going to say that, here is my initial moment. Here's my final moment. Just before it hits the ground, I can even draw the velocity just before it hits the ground. It'd be something like that. Actually, it should be pretty much equal to this one because they're on the same, they're on level heights right there. So I can, there you go. So there's the velocity right there. Let's see, what else do I need? I think that's it. Okay, so once again, one of the first things you want to do is that if you have what I call a misbehaving vector, so if a vector is pointing not in the x direction or not in the y direction, but multiple directions, then I have to resolve it into its component. So I got to break it up into its x component as well as its y component. So here's v naught y, there's vx. And I do know the angle. The angle is 30 degrees, and they told me the speed was 25 meters per second. So I'm going to cut to the chase here. You can do the trigonometry if you'd like, but I'm basically going to say for the y component, v naught y, or sorry, let's do the x first. So for Vx, it's going to be V naught cosine theta. And for V naught y, it's going to be V naught sine theta. So the convention is going to work, and you can double check that for yourself. So V naught cosine theta, it's going to be 25 cosine of 30, and V naught sine theta, that's going to be 25 sine of 30. So let's see, there we go, so sine of 30 is a half, and so that's 25 divided by 2. It's going to be 12.5 meters per second. And for the x component, cosine of 30 is a little bit more difficult. 0.866 is what I'm getting, times 25 is going to be 21.7. So this is 21.7. Meters per second, and there you go. And so I drew a diagram, I broke up any kind of, I resolved any misbehaving vectors, and then now I can fill in my Dix-Fixit and my Voiviagit. All right, so I already know from the acceleration of the moon, this is a free fall problem essentially, so the acceleration on the moon is negative 1.67 meters per second squared. Let's see. The initial velocity, that's right after it leaves the golf club in the y direction. I did calculate, it's 12.5 meters per second. And then we got the velocity in the x direction, that's 21.7 meters per second. Let's see, what else do I know? So, all right, so let's go ahead and do this. So let's see. And I also know the displacement in the y direction, right? If it started here and ended here, well, then the change in y that it did was 0. So this is going to be 0, and that's going to help me a lot. So I want to know how long was the ball in flight. So I think I'm going to use my beta equation, dy equals v naught y t plus 1/2 ay t squared. And then plugging in numbers here, I've got, let's see, displacement y is 0. Initial velocity along y is 12.5 t plus 1/2 times 1.67. So let me just, so negative 1.67. And then times squared. So this gets reduced to 12.5 t minus 1.67 divided by 2, which is 0.835 t squared. And then something I could do that you probably, so I might think, oh no, I got to do a quadratic equation. But hopefully, you know, in math you go, oh, well, t, I can factor out the t. I can factor out the t, so I do that. 12.5 minus 0.835 t. And then I can kind of solve for both these situations. So t equals 0. That it's telling me that's one. Right, I can solve these separately. Let me be more explicit about this. I'm going to solve this one, and then I'm going to solve this one. So I have one situation where t equals 0, and that's basically when the ball was down here, it was basically on the ground. So that's one situation right there. And then I can do the other situation, which is here, and I'm going to say 12.5 minus 0.835 t is equal to 0. And do a little bit of algebra. You get 12.5 divided by 0.835 is the time. And so that'll give me a number. I don't know exactly what it is. It's 12.5 divided by 0.835. I'm getting about 15. So 15 seconds. So there you go. There's part A. Okay. Now moving on. So there's part A. For part B, how far did it travel? It's asking for essentially how far that distance is. Well, I think I really only got one equation for that. That's Dix-Vixit in the x direction for how far it traveled. So let me draw that, my displacement vector. There's dx right there, my displacement vector. I also know that the acceleration goes that way. That should be in my diagram too. Okay, so Dix-Vixit. Dx equals Vx times t, or divot, basically. And so dx is equal to Vx, I calculated as 21.7. And then times the time, what did I go? Oh, 15. I got 15 seconds from over there. Yeah. So it's going to be 15 seconds. So I got dx is equal to 21.7 times 15. 40.5 meters. And then lastly, for part C, I think they say, what do they say? Ignoring air resistance, how much further would it travel on the moon than on Earth? So basically, I have to find out how this would work on Earth. Well, basically, the only difference is that my acceleration is going to be negative 10 now, again, meters per second squared. Everything else would remain the same. Nothing else is going to be changed by the fact that we're on Earth. So essentially, this becomes 10, which means this becomes 5. So this is 5. So this is 5. And that means this is 5. So it's 12.5 divided by 5. So that becomes 2.5 seconds it would be in the air. And then I could plug that all back into here. So it's 21.7 times 2.5, and I get 54. So I get okay, sorry, made a mistake here. I plugged in my calculator 2.17. So my bad. Let me recalculate that. Hopefully you caught that. 21.7, that's 326. So 326 meters right there. And then if I plug in 21.7 times 2.5 for Earth, that's going to give me a dx of 54 meters. So you can see much bigger. I can find the ratios, but what does exactly want me to do? How much further? So much further, almost 300 meters further on the moon. That's because, and that's where I caught myself, because I ended up plugging it in. I got a number that was bigger than what I originally had. Right, what I originally had. And so I was like, oh, that can't be, because the moon has less acceleration, so the ball is going to be able to be in the air longer without having to change its direction. Where on the Earth, it's got a much bigger acceleration, so it's going to fall faster. Yeah, so okay, hope that helped. Bye.